I am Lakshmi Prasanna, Assistant Professor, Department of ECE, Institute of Aeronautical Engineering. Welcome to the lecture session of image processing. In this session, we will discuss about basic gray level transformation. So, the topics what we are going to cover under that are piecewise linear transformation functions. In that, we are going to see three types. One is contrast stretching, gray level slicing, which is also called as intensity level slicing, and another one is bit plane slicing. So coming to this piecewise linear transformation function. So before this piecewise linear transformation function, we have seen four different types of intensity transformation function. So that four intensity transformation functions are point transmission, linear transmission, log transmission, and power law transmission. So those comes under intensity transformation function. But here this power law transformation function is somewhat different compared to that. So here this piecewise transformation function have some advantages and disadvantages compared to the previous four functions, that is intensity transformation function. So the advantage of this piecewise linear transformation function is less complex, it is less complex, and the disadvantage is it requires more user inputs. So compared to that four, this piecewise linear transformation is having its own advantage and disadvantage. So this piecewise linear transformation function can be applied for contrast stretching, or for gray level slicing, or for bit plane slicing. So first let us learn what is this contrast stretching. So whenever we capture the image, the captured image may be a low quality image due to some noise present in that, or due to lack of dynamic range in the image sensor, or it may be due to the lens aperture during image acquisition. Maybe the lens have been set in the wrong way. So all these are the different reasons for making the image that is acquired with low quality. Now, so in order to enhance that particular low quality image, we need to apply this contrast stretching. So if we apply the contrast stretching, it is going to increase the dynamic range of the gray levels in the image that is being processed. So the contrast stretching function will be represented as S is equal to T of R. So here this R represents the pixel value of the input image, and this S represents the pixel value of the output image, and here this T represents the transform what we are going to apply on the input image, which is also called as operator. Now, so here based on this function, we can observe here graph. So this x-axis represents the intensity pixel values for the input image, that is R, and this represents the output pixel values S. So now in this graph we can observe there are 2 points. One is R1S1 and another one is R2S2. So if we apply transform on the input image R, we are going to get some graph like this. It consists of 2 points R1, S1 and R2, S2. So the shape of this graph will be modified if the value of this R1, R2, S1, S2 changes. Now we will see how this particular graph will be modified based on the values of this coordinates R1, S1 and R2, S2. So we will see different cases with the values of R and S. Now consider case 1. So in this case, we can see here R1, S1 and R2, S2 are the 2 points. So if the value of R1 is equal to S1 and if the value of R2 is equal to S2, the transformation is a linear function that produces no change in the gray levels. That means here consider the value of R1. So this is R and this is S. So the value of R1, consider for example L by 4, this is, and here R1 is equal to S1. So the value L by 4, S1 is also L by 4. And consider the value of R2 is equal to S2. So for example, consider the value of R2, okay, 3L by 4, same will be S2. So if the value of R1 is equal to S1 and R2 is equal to S2, the graph will be a linear function. For example here, so the value of R1 is 1. So L by 4 means, so this is L by 4. So here you will get that point. And here R2, S2 same means 3L by 4. So here where is 3L by 4? So this is the point 3L by 4. So if we join these 2 points, we are going to get a graph like this, which we will call as a linear function. So in this case, there will not be any changes in the gray levels. That means the pixel value intensity will not be changed. It will be as it is. So this is one case. And coming to that means as we have discussed, if the values of R1, S1 and R2, S2 changes, we can observe a change in the curve which shows the intensity values of pixels. Now, so in the second case, if you see different values of R1, S1 and R2, S2, so in this case, R1 is equal to R2, whereas S1 is equal to 0 and S2 is L minus 1. So for example here, S2 is L minus 1 means this is L minus 1. This is L minus 1. So generally here you will have S2. So this point will be here. And S1 is equal to 0 means it will be on the x-axis because S will be 0 on the x-axis. And R1 is equal to R2 means let us consider some value of R. Either L by 4 or L by 2. Okay. So let us consider here it is L by 2. So L by 2 means here we will have. Now, how will be the, if you join these 2 points, how will be the curve? So from here to here, okay. So S2 is L minus 1 and R2 is also L by 2. So this is L by 2, which is the value of R2, and here H2 is L minus 1. Like this, we are going to get the graph. So in this graph, as we have discussed in the previous slides, if this is the case, it represents it is a binary image. So here it is given. In such cases, whenever the values of this R1, R2 and S1, S2 are selected in this manner, then after applying this piecewise transformation function, the output image what we are getting will be a binary image. And this value we have considered here is a value of R1 and R2. And coming to the third case, so in this case, the value of R1 S1 is equal to R minimum comma 0. That means R1 is equal to R minimum. Here this is the axis of R. R minimum means it may be any value of R, that is minimum value of R, and S1 is equal to 0. So minimum value of R means it will be R minimum, which is equal to 0. So we can have here at this point S1 is 0 anyway. And next one, R2 and S2 will be R maximum and L minus 1. So here this is L minus 1 point, and R2 is equal to R maximum means this is the only point. Again we will get the value of R2, which is R maximum. So obviously the curve what we are seeing here, after applying this piecewise linear transformation function, we are going to get like this only. So it denotes the minimum and maximum gray levels of the image. So the transformation function stretches the level of intensity from the original range to full range. That is, original range is 0, full range is L minus 1. So we have seen three cases changing the values of R1, R2, S1, S2, how the values of intensity values of pixels will be changing. Now, so based on what we have discussed till now, we can see here in this image, this is the transfer function, what we have discussed till now. So it is a form of transfer function. What type of transfer function means? Piecewise linear transformation function. And this is the input image or original image which is acquired by the sensor. Now, on this input image, piecewise linear transformation should be applied. So if this piecewise linear transformation is applied, then the image what we are going to get here is one case. So here this is case 3, and here this is one case as we have observed binary image. So in case of case 2, we have studied for different values of R1, R2, S1 and S2. So this is how we are going to get the images for different values of R and S. Now, coming to the second transfer function, which is gray level slicing. Gray level slicing can also be called as intensity level slicing. So what is the purpose of this technique means? It is going to highlight a specific range of intensity level in an image. That means it highlights only a particular part of an image on which we are interested. So this type of transformation can be applied in applications like X-ray images. For example, in X-ray images, if we want to identify any flaws in the X-ray images, that flaws will be highlighted with a specific range of intensity values. Only that particular flaw will be highlighted. So if you go for the second application, satellite images, for example, in the satellite images, if you want to highlight a particular area, for example, on the satellite images, if we want to highlight water bodies on the satellite images, that particular water bodies will be highlighted with a specific intensity. So all those are the regions of interest where the intensity levels will be highlighted. So this gray level slicing will be used in particular applications where we need to identify a particular interest. So this gray level or intensity level slicing can be done by using two approaches. So here the two approaches are, in the first approach, we can see display a high value of all gray levels in the range, and it is going to compress all the remaining values. For example, if we consider this graph, so if we consider this graph here, A and B, this is the region where the highlighting will takes place, whereas before this A and after this B, we will have low values. That means that intensity will be compressed. Coming to the second approach, here again we have A and B. That means, for example, in this case, only the highlighted area what we want will be visible, whereas the remaining will be compressed. In the second approach, the area what we want to see will be visible with high intensity, whereas the remaining areas, here you can see, the remaining areas will not be totally compressed. They will be preserved. Okay. So in this, only highlighted area can be visible, whereas the remaining will be totally compressed. Whereas in this approach, the area what we are concentrating will be highlighted, as well as the remaining areas will also be preserved. So these are the two approaches in this intensity level slicing. So in order to clearly understand this, we can see here this figure. So this is the original image. Okay. So this is the image of a blood vessel. If we are doing this intensity level slicing by following approach 1, so what is approach 1? We can see here, in this approach 1, high value of, it will allocate the high value for all the gray levels which are in the interest, whereas it will allocate low value for the other gray levels. So if you see here, this is the image for approach 1. So in this case, if you see, this is the blood vessel. Here only that particular blood vessel is being highlighted, whereas the remaining areas are totally compressed. But whereas here, if you see figure 3, this is by following approach 2. So approach 2 means, along with the highlighted value, the background also will be preserved. So along with this blood vessel, so the background is also preserved. So these are the example images for intensity level slicing. And the third transformation function, the third application in this piecewise transformation function is bit plane slicing. So in this bit plane slicing, so previously what we have seen is intensity level slicing. In the intensity level slicing, we have highlighted a particular area in an image, whereas in the bit plane slicing, not only particular area, the entire image will be highlighted. So that is the major difference between intensity level slicing and this bit plane slicing. Intensity level slicing, it is going to highlight only particular area in an image, whereas in the bit plane slicing, it is going to highlight the entire image. So instead of highlighting a gray level ranges, highlighting the contribution made to total image appearance by a specific bits may be disallowed. That is what we have discussed. Now, so this is the bit plane representation of 8-bit image. So here we have considered 8-bit image. So these are all the 8 planes. For example, so if for an 8-bit image, L is equal to 2 power k. So it is represented as 2 power 8. The total value is 256. So it will be ranging from 0 to 255. So here totally we will have a pixel values ranging from 0, 1, 2, so on here up to 255. So in this bit plane slicing, each pixel will be again represented by following 8 bits. So for example, if we consider this 2, it will be represented as 8 bits. So here 1, 0, value is 2. So in order to represent that using 8 bits, it can be represented like this. Whereas this bit is called LSB and this bit is called MSB. Okay. So this is what here it represents bit plane 0 and this represents bit plane 7. So all these bits will be represented in each of these bit planes. Here bit plane 0 consists of least significant information, whereas bit plane 7 will consist of most significant information. So whatever the information that is stored in all these bit planes cannot be observed clearly, whereas the information that is stored in this bit plane 7 can be clearly visible. Now, so as we have explained in the example, if we consider any 8-bit image, each pixel will be represented again with 8 bits. So each bit will be allocated to one bit plane. So bit plane 0 will be holding LSB, least significant bit. Bit plane 7 will be holding MSB, which is most significant bit. So as it is holding least significant bit, bit plane 0 contains all the lower order bits and bit plane 1 contains all the higher order bits. So in this we can clearly observe the difference, how the image will be observed on each bit plane. So this is the original image. So this image is stored on bit plane 1. So if we consider as what we have learned, that is 8-bit image. Okay. So in the bit plane 1, this is the image that is stored, and bit plane 2, this image will be stored. So if we consider 1, 2, 3, 4, 5, 6 bit planes, there is no much information stored on these bit planes. If we consider bit plane 7, this is somewhat better, but most important information will be stored in this bit plane 8. So this is very important. So these are the 3 applications in this piecewise linear transformation functions. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.